Hello everyone, and welcome back to the ANSYS Discovery Learning Track for Topology Optimization. In this video, we'll be reviewing how to tailor your results by specifying optimization objectives and manufacturing constraints. Let's get started. First, let's review our different optimization objectives. We can review these by opening up our topology optimization heads-up display by double-clicking the object in our physics tree, or simply right-clicking and then choosing Edit. The left side of our heads-up display gives us the opportunity to control our optimization objective. By selecting this drop-down, we can see our potential options. Our first and default option is to maximize stiffness. This will use iterative static analysis to maximize the stiffness or minimize the compliance of the model. It will reduce the volume to our primary target of volume reduction, but will also target the maximum stiffness possible for the remaining structure. Our next option is to maximize the natural frequency. This option uses iterative modal analysis to maximize the natural frequency of the part, specifically the first mode. Once again, volume reduction is our primary target. Balanced stiffness and frequency uses a combination of static structural analysis and modal analysis to maximize both stiffness and the natural frequency. Once again, volume reduction is our primary target. Target natural frequency allows us to specify a specific frequency for the solver to target as a primary goal of the optimization. Volume reduction will not be our primary target like the three previous objectives. To change the frequency, you can simply enter in a new value, just like you can for volume reduction and other physics boundary conditions. Our second to last objective is minimize volume. Let's select that objective. As you can see on the right side of the heads-up display, our primary objective is either von Mises stress, principal stress, factor of safety, or a percentage stiffness reduction. In these optimizations, Discovery will attempt to create the lightest geometry possible that satisfies the primary objective that we have shown here. Our last objective is to minimize stress. This is similar to our first option of maximize stiffness, as it will once again use iterative static analysis to minimize the von Mises or principal stress, depending on what we choose. It will reduce the volume to our primary target, but will also target the minimal stresses possible for the remaining structure. Finally, let's review our manufacturing constraints, which are available on the right side of the topology optimization heads-up display. To display these options, we can simply click Manufacturing Constraints. As you can see, we have 5 manufacturing constraint options. I traditionally group these into 2 categories of controlling the size of the features in our optimized model and controlling the orientation of features in the optimized model. Let's first review the min and max thickness options. These 2 features control the size of connected parts. To enable one of these manufacturing constraints, we can simply click to enable the option, which will turn the icon blue, indicating that it is active. Additionally, you can see that we have a new item in our physics tree where we can enter a new value for this constraint. Next, let's review our orientation features of pull, table, and overhang prevention. For molding-based processes, the pull direction allows us to specify the direction that the optimized product will be removed from the mold. Please note that this does not include draft constraints that are traditional in molded parts. Enabling this option adds the item to the tree where we can double-click to open the heads-up display. In this display, we can enter in vector values for the axis of part removal. By default, we are also considering a bidirectional pull, but we can simply turn this off by clicking this option here. A unidirectional pull allows only material to be removed from one orientation. The arrow in this case indicates the direction which features will grow. Our next option is the table direction, which is functionally the same as a 1D pull. This option is great for multi-axis milling processes. The arrow once again indicates the direction in which features will grow, or simply, it's the direction that is pointing towards your mill. To better help illustrate these options, I have prepared a few models on the screen. You can see how the parts differ in their features based on the application of manufacturing constraints. Our last manufacturing constraint is for overhang prevention. This is purely for 3D printing processes, as it will help reduce the amount of support material required during printing. By enabling this option, you'll be able to specify the direction in which the part will be printed, and additionally, you can add limits on your overhang angle. 45 degrees is a general best practice, but this will ultimately depend on your 3D printer. Thank you for watching this ANSYS Discovery Learning track for topology optimization. We hope that you found it helpful. Thank you and take care.